SwayamPrabha. Digital India. Educated India.
So students, today we will start a new chapter that's on interfaces, basically crystal interfaces and microstructures. That's correspond to the chapter 3 of the book which I prescribed you. In fact, whatever I am going to deliver lecture today is directly taken from the book of Porter and Easterling. So you can, if you want, you can directly refer to the book for details. Interfaces are very important for phase transformations, because phase transformation means formation of a new phase, many cases. So therefore, it involves nucleation and growth, and whenever you have a new phase forming in a old or parent phase, there is interface. But only discussing about those kind of heterogeneous interfaces is not going to give you the whole perspectives. That is why we start with the very basic concepts and slowly introduce the newer concepts. Things which will be discussed is basically what is the meaning of interfacial free energy. Then I will talk about different interfaces. First one, which is the most simplest one, is a solid vapor interface. Then gain boundaries, that is the boundaries in a single phase material, and one which I talked at the beginning, that is the interfaces in the solids. Finally, I will briefly touch upon what is the meaning of interfaces, interface migration, but that is the whole thing. Maybe it will be covered in next 2-3 lectures. So let us first look into what is the meaning of interfacial free energy. By the way, before I move, there are 3 types of interfaces which are important. One, as I told you, the free interfaces, okay, that is the vapor, and other 2 are actually either interface between the same gains, same phase of the same grains, or interface between the two phases. Whatever the situation, you are got to deal with interfacial energy. So whether it is a solid vapor interface or alpha alpha interface or its alpha beta interface, we are going to deal with boundaries, and boundaries will have energy, and this energy is always defined as interfacial free energy. This is a part of free energy which we have discussed, but different type of free energy. What is that? Free energy of system is basically, we always consider thermodynamics as a bulk thermodynamics. We never consider in thermodynamics the interfaces. So therefore, free energy is always given as a G of the bulk, that is where there is minimal effect of the interfaces. But the moment you have an interface, whether it is a surface or interface, we are going to have extra energy. The extra energy is basically coming from the surface area or interfacial area multiplied by the energy of the unit area. So that is basically nothing but surface area and a free energy of gamma, which is defined as a per unit area. So therefore, total energy of the system will be equal to G0 plus A gamma, because G0 is the energy of the bulk where there is no interface. The moment you are bringing into interface, you are going to add up A into gamma term, and A is the total area of the system and gamma is the surface energy of unit area. Now, so that means gamma is what? It is excess free energy. This is nothing but excess free energy which is coming because of the material lying at the close to the surface or interfaces. Okay. So please make it clear that this is a kind of a free energy, but this is excess free energy, something which is adding extra to the system. That is the main difference between free energy and the surface free energy. It will be there in any system where there is an interface or surface. You cannot actually completely ignore it. Only when we have a very large grain or very large, suppose material, the surface area is very small compared to the volume of the material, then you can ignore it, otherwise you cannot ignore these kind of things. So how do we actually calculate? There is a misconception between surface tension and surface energy. Let us be clear about the beginning. Surface tension is what? Surface tension is basically valid for the liquids. Now if I simply consider a frame, just like this on the right side shown. This is a frame you can see here, and in between the frame there is a thin film. Okay. Now, one of the bar of the frame is movable, other 3 bars actually are immovable. So, simply by moving this right side bar by a force F, I can increase the length of the this surface area of the film, because we are changing the dimensions. Okay. So, let us suppose if I apply force F per unit length parallel to this surface. Okay. So, what will happen? As the force will drive a small the thin film a small distance, because of that surface area will increase by a small amount, it is called dA, that is what I defined. So, because of this force, the work done is what? Work done is nothing but force multiplied by the how much is the surface area increase, that is F into dA. So, we know that dg is basically g0 plus a gamma that I have shown. So, dg is nothing but d gamma dA plus a d gamma, right. That is obvious, because g0 is constant, it does not depends on anything, it is basically bulk free energy. At a constant temperature pressure, this has no change. So, therefore, only change will happen on the a gamma, and if I total differential of a gamma is gamma dA plus a d gamma. So, if that is the change of the total free energy, that must be equal to the force multiplied by the area change, that is the work done. So, that is why if I equate that, F becomes gamma, you can clearly see this is a simple equation, not so very difficult one to understand. F is nothing but a gamma plus A multiplied by d gamma by dA, right. Now, for liquids, surface energy is always independent of the area, that I will explain why. That is why for liquid you always assume d gamma by dA is to be 0, and that is why F becomes completely equal to gamma. Why does it so? Because liquid is liquid is will not be able to support any shear stress. If you apply shear stress, liquid atoms will basically rearrange themselves, and that means the stretching of this film by application of the force F is nothing equivalent to like application of shear force on a liquid. Even if you stretch it, the atoms at the boundaries of the liquid will rearrange themselves, because there is a huge mobility, and because of that a constant surface structure can be maintained. There will be no difference between the structure of a liquid in the thin films in the center and at the boundary, because the rearrangement is very easy to possible. Because of that, the gamma will be independent of any change of surface area. Gamma will not change, because the atomic structure is remaining almost similar all throughout the thin films, and that is why in liquids the surface energy and the surface tensions are equal. But on the other hand, in solids, if I do the similar stuff, so suppose solid thin film, atoms movements are very slow, so therefore rearrangement is not possible, and therefore we cannot assume in a solid this d gamma by dA term to be going to be 0. That in fact for most of solids it is not equal to 0, and that is why in solids surface energy and surface tensions are different, and they are differed by this term A d gamma by dA. That is the major difference between solid and liquid. Okay, so that is very that is why in solid surface free energy and surface tensions are not identical. We have to know what is the dependence of gamma on surface area, okay, or stretching of that, and in fact that is what will be major discussion for the next few slides, which you will see. Now, question is this. To understand that, let us first assume in a solid, because liquid surface tension and surface energy is similar, there is no point in discussing about the liquids much. So, let us consider first a solid vapor interface, because solid liquid solid interfaces are little more complex. First we will consider solid vapor interface. Remember, any solid is in equilibrium with its vapor always. So, surface energy, let us suppose if I consider FCC crystal, that is very easy to understand, and this is what you see FCC crystal here. Atoms are sitting at these face center positions, right, and let us also suppose that surface is bounded by 111 plane of the FCC crystal structure, because 111 plane is the dense pack structure, a dense pack plane. So, therefore, let us suppose that, and we know that 111 plane obviously in FCC structure is a 12 coordinated atoms, all atoms are 12 coordinated. So, it is if you consider a surface of that, okay, if I draw it is down here, if I draw a simple one layer, simply it is one atom is surrounded by 6 atoms, correct, we can do that. Similarly, I can do the same thing here, this atom is surrounded by 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 atoms, right. So, all these atoms will be surrounded by that. Now, if you look at carefully in 3-dimensional space, okay, this is if suppose this is what is the plane of the surface, which is shown here by these yellow marked the yellow color balls, there are actually 3 neighbors out of 12 is absent on the top. That is understandable. So, if I consider that there are 6 neighbors on this plane, okay, and there has to be 12. So, therefore, at the bottom there will be another 3 and the top there will be another 3, because this is suppose in FCC crystal structure is ABC stacking, right. So, if this is A and the B layer will be somewhat like this, okay, one atom there, this was vacant, then another atom there, this is vacant, another atom there, right. So, and similarly the bottom also there will be another layer below that. So, if these 3 bonds are at the surface, that means 3 of the 12 bonds will be broken, that is very clear. Now, if the bond strengths, suppose let us assume this is a pure metal, okay. So, therefore, bond strength of every bond is similar, that is equal to given by epsilon. So, each bond can be considered as lowering the internal energy by gamma of epsilon by 2, obviously, because each bond is formed by 2 atoms. So, therefore, I have to consider that the lowering of the interfacial energy by epsilon by 2, because there are 2 atoms involved. So, per atom it is epsilon by 2. Therefore, every surface atom will with 3 broken bonds will have an excess energy of 3 gamma by 3 epsilon by 2, because the 3 bonds broken. So, 3 into epsilon by 2 is what is the excess interfacial energy, that is over the surface of the bulk of atom in the bulk. Now, how do I estimate epsilon? Simple way of estimating epsilon is related this to heat of sublimation, because it is a solid vapor. Okay, heat of sublimation means what? Solid is becoming a vapor phase. So, that means all the bonds in the solid state are broken and they are becoming vapor. That is why vapor there is no bond, I mean the atoms there are bonds, but weak bonds are there, but basically bond characteristics changing from solid to vapor when something sublimates. So, therefore, latent heat of sublimation must be equal to the sum of the latent heat or the equal to the sum of latent heat of the fusion plus latent heat of vaporization, that we know basically. First something has to melt, then it can vaporize. Now, let us suppose, forget about all this stuff, let us suppose you have 1 mole of solid that has vaporized. So, that means what? Total 12 into Na number of bonds are broken, Na is the Avogadro number. So, therefore, I can write down latent heat of this sublimation must be equal to total number of bond multiplied by the bond energies, that is epsilon by 2. That you can see is basically that gives you epsilon is nothing but Ls by 6 Na. That is simple order of magnitude calculation will give you this is Ls by 6 Na, that is Ls if I know, latent evaporation I know, and if I have 1 mole pieces, so then I can simply calculate the bond energies is equal to Ls by 6 Na. So, now if I have that idea, what I can do? So, assume that this surface energy is basically because of these 1 1 1 surfaces. So, therefore, that must be equal to 3 epsilon by 2 I have already considered, and epsilon is what? Ls by 6 Na. So, that gives me surface energy is equal to 0.25 into Ls by Na, right. If I simply do the calculations, basically you can see this is 12, this is 3. So, therefore, 1 by 4 and 1 by 4 become 0.25 and this is Ls by Na. So, that means different crystal will have different values of surface energies, solid vapor surface energies, because they will have different values of Ls, or rather the simple model allows you to calculate solid vapor interfacial energies simply by knowing the heat of sublimation. That is what is the important information you can take from this simple derivation, that if I know basically the latent heat of sublimation, I can calculate what is the solid liquid vapor interfacial energy. That is why in the literature you see initially from 1870s to about 1940s, there are extensive research work done on solid vapor interfacial energies, because this is very easy to conceive and understand. There is no difficulty at all, but things will change slowly. Now, how does it scale with the real experiments? That is what we will always like to know. Real surface energy is actually atoms. We always consider the whole derivation atom as a rigid sphere, and they are not able to move. These things are not actually correct, but there is another thing which we have not considered here. Surface atoms obviously will have more freedoms. Why? Because they are sitting at the surface, therefore their bonds are broken, they can move more than the bulk. Secondly, there is a higher thermal entropy to the surface atoms. Why? Because this extra configuration, because atoms are actually at some atoms they have no bonds. So, they can configure it more way than a bulk atom. In a bulk atom cannot sit, configuration of the atoms are more fixed, you cannot change it, but the surface it can be changed. So, because of this configuration variations of the surface atoms, I can sit with if I have surface atom, I can sit near a vacancy or near some other atoms, I can move also little bit because of thermal energies. So, because of that this excess entropy of configuration entropy will lead to change in the model. This model did not consider that. So, surface energy of crystal will be therefore associated with excess entropy term. That excess entropy we have not considered in our model, we simply ignored that. And because of that, because of you have a lot of freedom, more freedom, surface atoms have more freedom. So, that is why the configuration can be easily changed. That is why the values of gamma whatever calculated will be less than what we have calculated in the model, and people have seen the value actually is 0.15 multiplied by Ls by Na, is not 0.25. 0.25 is little overestimation compared to what are the assumption which you have made. So, if you clearly see that it is already given this value, this is again taken from the literature for the tin, aluminum, silver, gold, copper, delta iron, platinum and tungsten. So, you have basically FCC and BCC and tin is BCT, and depending on the melting temperature the values of gamma solid liquid vapor energy will change. Tin has the lowest melting temperature here 232 degrees Celsius, so it has about 680 millijoule per meter square is the surface energy, solid vapor surface energy. On the tungsten has the highest melting temperature about 3400 degrees Celsius, it has the highest value 2650 is the solid liquid centrifugal energy millijoule per meter square for the tungsten. So, therefore, it is obvious more higher the melting temperature has the bond energies, the higher the bond energies has the value of solid vapor interfacial energy. So, it is very easy to actually deal with solid vapor interfaces, okay, very easy. You can actually clearly see that simply by considering a broken bond model like this way we can get into the values, okay. Obviously, model overestimates little bit, but that can be even considered in the real world, correct. But reality is little bit even different. We have assumed what? We have assumed only a 1-1-1 plane which is the low index plane which is the bonding surface, or you can assume actually 1-1-0 planes. But if suppose all the surfaces will not be bounded by 1-1-1 plane, there will be reconstruct surface also. Let us suppose surface is bounded by odd plane or a irrational plane, okay. How do you deal with it? In such a case the broken bond model will still be applied, but we have to consider a different way. We have to consider the interface like this which is shown here, okay, which makes an angle cos theta here, okay. And so, or better let us consider the bottom picture broken bond model. What you see here, it is basically step surface, it is no longer a flat surface. So, if you have a step surface, because you have different kind of planes actually sitting on the surface, somewhere it is 1-1-1 plane, somewhere it is 1-1-0 plane, somewhere it is different kind 1-1-0 plane. Because different planes are sitting on the surface, so therefore bonds, number of bonds broken are also different, they are not same, okay, because the atom sitting on the top surface of 1-1-1 plane is different from the number of atoms sitting on the top surface of a 1-0-0 plane or maybe some other plane. So, that is why we need to consider such a generalized situation in which this broken bonds can be of different types on this surface, okay. Now, if I assume that there are two things we have to assume, it is not no longer a 2-dimensional surface, it is a 3-dimensional surface. So, there are bonds which are broken, which are parallel to the surface and perpendicular to surface, that is, this is the surface suppose which is on my screen of the projector, and also there is a surface perpendicular to that, okay. Obviously, it has gone into the into the plane of the board or the plane of the projector. So, because of that we need to consider bonds broken parallel to the surface and perpendicular to the surface. There are two type of bonds are there. Easy to understand. In any solid surface, I do not know whether I can show it to you. Oh, there is a duster. Any solid surface, if I consider like this, if this is my surface, okay, this is the parallel to the surface, this is the perpendicular to the surface. Okay. So, you can also have a bond broken on the surface and bonds which is extended. This is surface is like this, because this is the solid. The surface is bounded by this plane and this plane. So, therefore, we can not only consider two dimensional surface like this, we need to consider these ones also which are perpendicular, or these ones which are perpendicular to the surface. So, that is why we need to calculate total number of bonds broken, and as I said, this plane might be 1 1 1, but these planes may not be. Okay, this plane will be different types of planes. So, that is why we need to consider in generalized view, and the generalized view says that total number of bonds is basically bond broken is basically perpendicular number of bonds which are perpendicular to the surface, these surfaces, or parallel to the surfaces. I am not doing mathematics, okay, you can do that. Actually these mathematics are not difficult. If we do the proper calculations, total number of bonds will be equal to cos theta by a square, which are perpendicular broken in the perpendicular directions. If I have theta as the angle which the surface is making with the bulk, and similarly it is sin theta by a square for the parallel ones. So, that means what? We have a cos theta plus sin theta by a square. Remember, it is always put mod on sin theta, because sin theta can be more than 90 degrees and then it can be negative, that is why, but it cannot be negative, bonds broken cannot be negative, it has to be positive, that is why I always put a mod. So, then what actually happens? Then total surface energy is equal to n in multiplied by the epsilon by 2, and here n become cos theta plus sin theta by 2a square, or rather it becomes cos theta plus sin theta multiplied by epsilon by 2a square. Okay, now that means what? Interfacial energy is a function of theta. It is also a function of the A is basically A is the distance between the two planes, and that is the interplanar spacing depending on whichever plane. Actually that also you can change depending on the planes also, but we have considered average value of A, and epsilon is the average bonds energy. Okay, so now if I plot EASV versus theta, that is what you probably can do that in a two dimensional space. You can see basically it shows curves very clearly, it shows something goes increase and decrease and curves, and at 90 minus 90 plus 90, that is why sign is mod, at minus 90 plus 90 and 0, the curves has very low values. Basically these correspond to the low index planes. Low index planes like 1 1 1 or even 1 1 0 will have lower interfacial energy compared to the irrational planes or planes which are high index, suppose let us say 3 3 1, 2 2 1 or many other planes such like that. So, therefore, these curves has minimum or minimum points, and these points are very important, because these are the points in which surface will be lowest. So, therefore, if the system also decreases total energy of system, which is equal to G0 plus A gamma, the planes which will be bounded surfaces must be the ones which has the lowest energies, because A and gamma will be then lowest. Gamma is low means A gamma will be low. So, that is the basically main conclusion of such a kind of analysis for the solid paper interface. Conclusion is that there are curves in the free energy in the surface free energy plots, and these curves has minimum points and certain value of theta. Now, how we can do that in a, if I consider a complete crystal, suppose the crystal is such a kind of complex shapes you see here, can I do it a very simple way? Very simple way means very logical way. Well, what I can do, I can actually get gamma as a function of theta for all the curves. All the curves means all the surfaces. This is bounded by many surfaces. You see here these, so many surfaces. For each surfaces, I can do the similar analysis, and I can find out the surface energy, interfacial energy between solid and paper as a function of theta for each surfaces. Then I can plot. That is the outside plot you see here is a two dimensional plot. Remember, it's not 2D plots, although the crystal is 3D. So, it is a 2D plot just to make you sure that you understand things. You can always make a 3D plot, that is not a big difficult, but it requires a little bit more calculations. So, that is the 3 dimension, this is the cups, you see here the cups and minimum points here, you can see here the minimum point, that is the outside envelope. Now, and that is what is known as E versus theta plot, E is the interfacial energy, solid vapor interfacial energy. For the highest index planes, they can even actually, you can see, okay, let us assume, suppose you have isolated crystal which is bounded by many planes, that is what is shown on this, between this picture, and these planes have different surface energy areas A1, A2, A3 and different surface energies, that is gamma 1, gamma 2, gamma 3. So, total energy is equal to summation of that A1 gamma 1, A2 gamma 2, A3 gamma 3, that means it is summation of AI gamma I. Equilibrium says shape will have the property, okay, that is the very important thing which you should understand. Equilibrium shape, that means shapes which will be the minimum energy shape, it will have the property that this summation is a minimum, and the shape that satisfies this condition is given by what is known as Wolff condition or Wolff construction rather. So, virtually it says you that you must control, you must not control, you must select the planes of the crystal, bounding surfaces of the crystal such that the total gamma A is minimum. And you know, one can do it mathematically, that is not a very difficult task also nowadays, even with the advent of computers you can easily do that, but it is better actually do it by geometrically, and that is what is done by Wolff. What Wolff said, okay, let us do that. Suppose this is my cups, what I do, this is my center of the crystal or center of this plot, not the crystal, sorry, center of this plot, okay, this is what. Now what I do, I consider a point on these cups, okay, suppose this point is A. So, if I join this point A and this central point O, okay, let us join by dotted line, and then I do one thing, I simply draw a tangent to that, okay. So, that means I draw a normal to that, not a tangent, I draw a normal to these cups at this point. You can see this is what is that normal. Obviously, normal is what? This is my direction, and then I put a 90-degree line with respect to that. So, if I do that, that becomes my Wolff plane, okay. You can clearly see if I transpose this here, that is what it is. So, on each of these points I can do that, I can draw another line here and I can do that, okay. I can do another line here, I can do that. This is what is done, correct. So, on the whole this gamma plot, that is E versus theta plot. Now, once I do that, the inner envelope what will be forming, inner envelope will be like this, what is shown here is what is your equilibrium crystals shape, that is what is Wolff's construction shape tells you. But it assumes one thing, that means the interfacial energy of these planes is parallel, is proportional to this length of the normal, length of this length I have drawn from O to AA, this length is what is proportional to the interfacial energy, that is what is inherent assumptions, okay. This is written here. So, here OC, C is here, you see here OC, C is here, okay. OC is equal to gamma 111, why? Because this point corresponds to 111 plane, there is a minimum point in the cups, that must be 111 plane. So, this distance is proportional to 111 surface energies. If this is 110, this distance will be proportional to 110, gamma 110, okay. That is how we can calculate, you can actually get a ratio of the surface energies of each of these planes. So, that is actually let us stop it here. So, that is the way actually solid vapor interfaces are dealt with. Now, in the next what I am going to do it is a little bit different, okay. This is shown here again in a much better way, basically same thing is shown here in a bigger picture, not a different thing. Now, in the next class what I am going to do is I am going to talk about gain boundaries. That is solid vapor interfacial energy is what is the easiest thing to understand. You have a solid and you have a vapor around it. But if I have two grains, solid and solid, same chemistry, what is the type of interfaces it can develop, that we will deal in the next lecture.